UNSW and I organised for 2013, and we're doing it again for 2014. I hadn't intended to advertise this now, but because someone mentioned it 2 or 3 minutes ago, I thought I'd just pop that up and let you know about it, because this may appeal to the people in the room. So there you go, a second NICTA Software Systems Summer School, and basically it involves about half a dozen or so top overseas people coming and giving keynotes, and PhD students or anyone else talking about their research in lightning talks. Now, I'll just check the microphones before I'm just going to mute out everything except for Gooseneck. There we go. All right, and I'll start my, here we go. I'm going to record it myself. Maybe. Okay. All right, thank you very much. So three thank yous I'd like to say before I start. First of all, thank you for actually getting out of bed at 10 o'clock on a Sunday, or getting out of bed sometime before 10 o'clock on a Sunday to come and hear this. That's really impressive. I'm impressed and congratulate you all on that. Thank you all for inviting me. I'm really honoured to be here. I really enjoyed preparing this talk, and I'm really looking forward to giving the talk and talking to you all later. So thank you for that. And finally, I want to get all of you to thank the organisers. I think this is really amazing that they've organised this conference, and I'd like to thank the organisers for actually taking the initiative of organising this thing. So thank you to the organisers. All right. So hopefully none of you are too precious about your sacred cows, because they might get skewered in the next hour. But if your favourite language hasn't come up yet, don't get too smug, because maybe I'm about to skewer it next. Or maybe I'll leave that for another talk. There's an awful lot of languages out there. So this talk is really about the main focus of my research. In the next 50 minutes or so, I'm going to start with a big picture, start with stuff that's fairly easygoing and comfortable. I'm going to motivate why I think most languages suck today, talking about what I mean when I say that they suck. Now, is that audio okay, or it sounds like it's not so great?
Use the lapel mic.
Yeah, I normally actually speak every week in this lecture theatre twice, and I use the gooseneck, but just now I hear a strange sound, so I'm going to switch to lapel mic, which was not the game plan, but I'm going to do that. Yeah, so I'm very comfortable speaking in this theatre. Some lucky souls here get to hear me twice a week in this very room. All right. Yeah, that's on, but I've muted it here. Lapel, unmute. All right. Can you hear me now?
Yeah.
Yep. All right, let's keep going. All right, so towards the end of this talk, I'm going to dive a bit deeper. I'm going to go into some very recent research. And your eyes may glaze over. Some of you might really get into it. Others of you may not so much. That's okay. There'll be other parts of the talk, hopefully, that you all enjoy. Now, I wanted to make this talk up to the minute. I want to include information here that is recent. I've got research results that are just being published, things like that. So I've tried to keep things very fresh. And speaking about up to the minute, here's a little anecdote from last night, very up to the minute. So my preschool-aged daughter is at the dinner table, and she's reciting arithmetic facts, as preschool-aged daughters tend to do. And she's going, 2 + 2 is 4, and this sort of stuff. Well, she actually asked the other members of the family, and they obligingly have the answer. And then she says, hamburger plus goo-goo. And the rest of the family, including her 10-year-old brother, start rolling their eyes. And then she says, what is it? And then the other sister said, you tell me, what's the answer? And she says, it's goo-goo. And so why? Well, it's the last thing that I said. And so everyone rolls their eyes. Okay? And I guess the moral of that story is that if you're creating the game, the rules are yours. You can make whatever rules you want. So to heck with commutativity or anything like that, if addition means precisely what you want it to mean if you're making up the rules. So that was the takeaway I took from dinner last night. How does it relate to this talk? Well, we'll come to that in a minute. Anyway, this is the first thing I'll start with. And I was amused just the other day to notice someone had actually gone and produced a WTF graph of programming languages. And they did this incredibly scientifically by searching for the string WTF in repos. All right, so it's a joke, but it is real data. It doesn't really mean very much, though. But the general idea is that people find some languages very hard, very inscrutable, hard to reason about, and sufficiently so that people write about this, and there's humor around it. So let's move on and actually look at some specifics. Now, can you see it okay? Yeah, okay, all right. So we're going to look at some JavaScript. Who here has written any JavaScript? Oh, okay, so you guys are going to get all this right. Okay, this is a quiz, right? So, array plus an array. What's the answer? Anyone? 2. 2? All right, I hear 2. Anyone else? Sorry, you're wrong. Empty string. Right, okay, so I'll try again. You guys are supposed to be the JavaScript experts. I'm not a JavaScript expert. Array plus object, what's that? Sorry. Object. All right. Now. Exactly. and then we have object. Some of you have seen this before. Object plus array. All right. So much for commutativity, right? And then finally, object plus object. That's kind of obvious, right? Well, it's definitely not a number, okay? All right, so some of you have seen this before, but I'll just run through it anyway. So that, hopefully, well, some of you may know what you get if you type that in. What do you get? Well, you get an array separated by commas, a comma-delimited array of nulls, okay? So that's what that looks like, okay? I don't know why the commas are there, because they're not there when you do other things. But anyway, the commas are there. This is what, you can try this out if you think I'm making this up, right? What about that? Sorry, no. Very good. the commas disappear, of course, and we get foo, 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 all right? And what about this? Yeah. All right, and then this one? Someone got it. All right. So enough taunting JavaScript and its craziness. Let's move to something more serious, because JavaScript's just client-side, PHP server-side. Let's look at something a little more serious. We'll look at some PHP. Okay, so you all know what this does, right? Well, who does PHP here? Who's familiar with PHP? Right, so you're the guys I'm going to be looking to for the answers, right? Okay, so here we create an array, A, and we initialize the first element, the 0th element, with 5, and then we print out that string now, right? So what do we get? We get that. Okay, everything okay? Everyone comfortable with that? All right. So what happens if we do this? Okay, so we assign A to C, and then we set C sub 0 to 10. What do we get? Anyone? Well, come on, you guys are PHP programmers, you know this.
5.
Very good. Why do you get 5? Anyone?
It copies it.
Why?
I don't know.
All right, this is why. This is straight out of the Docker. All right, so arrays are treated as values in PHP, which seems very strange to many people, but they are. They're treated as values. Arrays are treated as values. How do you actually implement this? Well, this is kind of crazy, and as the person in the back correctly pointed out, to actually implement this correctly, you need to copy, right? Okay, so you copy A. You make a copy every time you do it. Right, that sounds insanely expensive. But no, the PHP implementers were very, very clever. And what they did is they only copied when they really needed to. So it just looks like it's copied. It doesn't actually copy unless it needs to. Right? Everyone with me so far? Because they're very clever people. They do this stuff, right? So now let's have a look at something a little more interesting. All right. So you know what I just added there? I said B is a reference to the 0th element of array A. All right? And then we just have the rest of the program as it was, right? right, this is for real. Okay, does anyone have any idea what happened here? It's PHP, yeah. All right, what happened here was that because you've taken a reference to the element, it gets boxed. It gets ripped out of the array and turned into a box, okay? It gets boxed. It's turned into an object with a reference to it, okay? And then what happens is you then copy the array, you copy the reference, and then when C goes and changes element 0 to 10, it actually changes the value inside the box, which is also referred to by A, and when you print out A, you get the 10. Perfectly sensible, right? All right, what about this? No, that's, no, not null, but that was a good guess. All right. Okay. Why is that? Because once you delete that last reference to that element, it gets unboxed back into the array, and then when you copy the array, you just get the value. All right. This is completely sensible, right? All right. So someone, can you read that? I don't know if you can read that, but anyway, so someone made a point of this in a bug report back in 2002, and they weren't very happy about it, right? They said, this is crazy stuff. And anyway, there's a long discussion. It took ages to resolve. But finally, here's the answer, right? Can you read that? I'll read it out for you. We have discussed this issue, and it will put a considerable slowdown on PHP's performance to fix this properly. Therefore, we'll document it. All right? So... all right, enough making fun of languages like JavaScript and PHP. It's not very fair. Oh, before I do that, look, this is before I stop making fun of PHP. So this issue is so bizarre that it was worthy of a Popple paper. If any of you are PL heads here, you know Popple is the top conference for the theory of programming languages. So there's a Popple paper in 2009 which you can go and read and understand that little bit of code I just showed you. You can read 10 pages all about it with lots of proofs. All right. Now, Java. Okay, I'm not going to say very much about Java because you all know about Java. So what's wrong with this? Well, you all know what's wrong with that. You can't do this, right? You can't do this in Java. Right? You can't have value types as with generics, right? You can't use value types with generics. Why not? Does anyone know why not?
They're not objects.
Well, yes, because they're not objects, but why can't you have something that's not an object?
They don't derive from objects.
Well, because they don't derive. This is true, but why is this a limitation of Java? Does anyone know the answer to that? Essentially it's pragmatic. It's how they implemented it, okay? So it's a way Java, putting it differently, generics were retrofitted to the language, okay? And they had a choice, right? They had a choice. Essentially the choice was do it right or do it easily. No, well, that's not fair. That's not fair. They had a choice, do it right or change the JVM, the actual JVM, okay? And they really didn't want to do that. Okay, they really didn't want to change the JVM. And to do it without changing JVM, this is what they had to do. Okay? So they had their hands tied behind their back. They felt they did, right? They felt they had no choice but to go this route. On the other hand, you can't read that either, but there is a fantastic paper, 2001 PLDI, Andrew Kennedy, Don Syme. This is how you do generics properly. And this is done in .NET. For those of you who are in my class, you'll have heard me say this before. Don Syme is an ANU grad. He did honours here, and then he went on and did his PhD in Cambridge, and then went to Microsoft Research. But he was the guy who, with Andrew Kennedy, nailed generics for .NET, and they actually did it properly. Okay, Microsoft has an advantage because they just decide that if they want to change .NET, that they can. They don't feel quite so compelled by the mood of the community. So they had more liberties, if you like, as designers, and they did it properly. Okay, so there's a double-edged sword, right? Anyway, so there you go. I've just given you 3 examples of 3 languages which you're all fairly familiar with, which are just totally ridiculous. Okay, and for different reasons. Okay, so that's all about WTF, if you like, that last part. Now, what about security and correctness? Most of you will have heard about this stuff before. I don't need to tell you too much, but, you know, oops, I'll just let you see that. That was a bit too quick. That was from 2 days ago, 3 days ago. Okay, Java exploits seen as huge menace, blah, blah, blah. All right, critical PHP vulnerability, blah, blah, blah. JavaScript vulnerability, Java 0 day, yeah, PHP badness. All right, lots of nasty things happening. Okay, well, what's going on here? Well, there are a lot of things going on here, but one take on this is that we've got a double-edged sword with languages like this. These languages, what they're offering you is a rich set of libraries, right? A whole lot of libraries. That's one of the properties of these languages compared to a language like C or Fortran or whatever. They've got this big set of libraries. They have built-in safety, right? So they have a whole lot of safety built into the language. They have strong abstractions. They abstract over memory, for example. And they have abstractions. Some of them have abstractions for concurrency. And all these things mean that there's less chance for programmers to make errors, which make them popular, okay? But in doing all that, the language itself becomes a juicier target, okay? So the language becomes a more open target for attack. So this is a real problem and a real headache for people like Oracle who are trying to deliver a safe Java implementation. Anyone who's in that game, it's a real headache, okay? Because obviously, the more abstractions you present, the richer the language is, the bigger your attack surface, and the more exposed you are. Okay, let's look at performance. Okay, so for those of you who don't know, this is one of my main things, is doing performance analysis, understanding performance of languages and all this sort of stuff. So I take very seriously how you measure and how you compare programming languages. Okay, very serious stuff. So what I'm going to show you today is not serious at all. What I'm showing you here is from the very famous benchmark shootout website, which I don't know if you can read in grey that little URL down the bottom there, but there's a URL. Who's seen the benchmark shootout website? It's a pretty popular website. It's very cool, and the person who wrote it really does know what they're doing, and it's just covered with disclaimers pointing out that this stuff doesn't mean very much unless you really understand what you're looking at, and most people don't. Okay, so take this with a grain of salt. But what do you see here? You see a log scale, right? You see a log scale, and you see languages out there which are 100 times slower than the languages on the left. Okay, languages on the right, 100 times slower than the language on the left. That's just some benchmark in the shootout page. Here's another benchmark, Mandelbrot. Same deal. You got languages on the right there which are 200-300 times slower than the languages on the left. Here you're getting close to 1,000 times slower. That's serious slowdown. 1,000 times. Okay, some people might notice that. Okay, and then here, this is completely different. This is actually more serious analysis. What we're doing here is this is from work my recently graduated PhD student. Actually, she hasn't graduated. She's being examined right now, but she's just finished. Ting, she did this work here where she's gone and done a very detailed analysis of where the cycles are being spent in Java benchmarks. And you see the dark blue there is when optimized code is running. So that's ostensibly just the application, optimize the heck out of the application, and that's our optimized code running. The light blue is essentially the interpreter running, and then the green is the JIT, which is optimizing the code for the dark blue stuff, and then the orange is the GC. And there's a set of benchmarks there, and then you can see on the left there, you can see the average. But what you notice there is you're getting, what is that? That's 37%, right? So between 1/3 and half of your cycles for these benchmarks is going towards the abstractions. Okay, so we're providing all these abstractions. The JIT, which is providing abstraction over the computer architecture. We're providing the GC, which is providing an abstraction over memory, and so forth. But this doesn't come for free, right? It's costing you. And this is a very optimized system. This is not Perl we're talking about here. This is a highly optimized Java system. Okay, and still you're paying 37%. Right? This is a serious cost. All right, so why? First of all, what's so hard about all this? I mean, really? Well, first of all, there's a JIT. You need to be pretty smart to write a JIT, okay? Seriously smart. Anyone have any idea how many lines of code there are in a good JIT, like the one in Hotspot or, say, the one in .NET or the similar sort of thing? These things in the ballpark are 100,000 lines of code. That's the sort of size we're talking about. How many PhDs went into them? Maybe 10, maybe 20, maybe 50. So very, very serious amount of intellectual investment in a JIT. Similar sort of story with concurrency, smaller code base, non-trivial subject matter. How do you concurrency right? How do you do scheduling right? How do you make sure your threads behave correctly? All this sort of stuff. And finally, garbage collection. There's an entire literature on garbage collection. There's over 2,000 papers, there's textbooks, and so forth and so on. All sorts of stuff on garbage collection. How you get garbage collection right. Okay, so if you want to build one of these languages right, you need to master all these things, right? That sounds hard. But it gets harder because when you bring them together, each of these interact with each other, and you actually get something like a cross product. You get this explosion this complexity explosion. Okay, you can't build a GC that's not concurrent. Okay, and your GC has to also be aware of the JIT. And so forth. These things all have to be aware of each other. And it's really, really seriously hard, okay? So part of the explanation to what you just saw is actually implementing programming languages is hard, and doing it well is hard. So here's a quick look at a few programming languages on the left. This slide here is courtesy of one of my current PhD students who came to ANU trying to make, his goal in life was to make Python go fast. Anyway, this is an analysis of a handful of existing dynamic language runtimes and where they're at with respect to the JIT, concurrency, and the garbage collector. And roughly speaking, red means it really sucks, green means it's okay, and orange means it's not real great. Okay, so it's a pretty ugly story. Most languages are interpreted; they don't have aggressive JITs. Most of them don't have a very good story with concurrency. Some of them have this GIL, the infamous GIL, the global interpreter lock, this big fat lock that locks everything synchronizes around. And a large number of them have this horrible, what's called naive reference counting. Naive reference counting is an appallingly slow algorithm which simply counts every single mutation to every pointer in the program, which was given up by the serious GC community, I don't know, 30 years ago. But a lot of these languages use it today, believe it or not. All right, so that picture there is just to try and paint a picture for you of how ugly current implementations are, and the previous slide was there to give you a clue as to why they're like that. All right, so I don't know, who's seen this photo before? Anyone seen this before? Okay, someone's seen it before. Okay, this is a very famous photo from a very, very famous experiment, one of the most famous experiments in psychology. The experiment goes like this. I forget when it was now. It might have been in the 70s. It was done at Stanford, and the way it works is you get small children, and you put them in a room with the mirrored glass and the camera watching them, and you put a marshmallow in front of them, and you tell them, if you can sit here and look at that marshmallow and not eat it, I'm going to give you 2 marshmallows. All right? This kid here has been sitting there for like 1 minute and 50 seconds. And he's killing himself. There's that marshmallow right in front of him. He so much wants to eat the marshmallow, and he's going to see if he can hold that extra 10 seconds. Anyway, I think you can find this stuff on YouTube. It's just hilarious watching these kids. There's some of them, of course, the sneaky ones try and eat the stuff from inside the marshmallow and put it back on the plate so no one will notice and stuff like this. But it's good stuff. Okay, so where's the connection? All right, I've lost you completely. The connection is this. If you're the person who's come up with a new programming language, do you really want to sit around and try and get a PhD in garbage collection or JIT compilation? Of course you don't, right? You want to write the flipping thing. You want to build the language and be done with it, right? You want to do it now, okay? This is about deferred gratification. That's what this famous experiment was about, deferred gratification, holding back and getting something better by holding back. Software developer, programming language implementers, programming language designers seem to be incapable of deferred gratification. They want to dive in, build the thing immediately, as fast as they can, and to heck with the consequences. Okay? And I just showed you a couple of examples of where that's happened, right? It gets worse. Right, so this is the motif, if you like, of a whole bunch of my work these days. It's about deferred gratification. So what happens, right? So you build this language, and this is the language, and you know you've got a fantastic idea for a language, and you're going to go build it. It's going to be called Python or something, and you decide, okay, I don't really want to learn how to write a JIT, so I'm just going to build an interpreter. Okay, so we don't really need a JIT, right? And then you decide, well, concurrency, well, we don't have multi-core computers yet. I don't know what multi-core is yet, so we won't worry about concurrency, right? And then GC, that's just for wimps, right? Well, no, we can build a reference counter. Reference counting will do the trick, a plain old reference counter. And then you end up with a language somewhat like that, okay, for your first implementation, all right? Okay, so I overstated it, right? You end up with that, okay, because you can fix a bunch of stuff, but you can't fix it all. And that's the point. The thing that's I found alarming when it finally sunk into me is the extent to which these decisions that happen early on when you're building those first prototypes actually get baked into the language semantics. They're there forever, okay? How did I come across this? Well, we did some work on reference counting, which I'm going to show you shortly. And people at Facebook were pretty interested in it. Now, they are pretty interested in it. We're working with them now on it. And they're interested in it because they depend on reference counting. And we had the stuff that makes reference counting go massively faster. So they're interested in this. And I started pushing them on why they use reference counting, and essentially the answer is, and that the example I gave with the PHP before is a classic example of it. The fact that you have a naive reference counter in your implementation is visible to the programmer in the language semantics. Okay, so the language actually dictates through its semantics a very specific implementation choice, and a really crap choice at that. Okay, this is baked into the language. No getting away from it. Okay, so the only way to break away from that is to change the language. Okay, and that's ultimately what people will have to do if they want to get away from it. But the point I'm trying to make is that, yes, I'm all for rapid prototyping and do it quick and dirty first time through, but you have to be very careful, because if you make the wrong decision, you'll end up cooking your language and it'll be there forever. Okay, so what are the current approaches to building languages? Well, there's the classic monolithic approach. I'm just going to build the whole thing from scratch myself, all right? That's pretty standard. There are people who build languages on top of JVMs and .NET, okay? So anyone have any idea what the problem with that is? It's very, very popular, so this is a good idea, right? What the obvious advantage is you get a GC for free, you get concurrency, and you get a JIT for free. Yeah, awesome. But any problems?
You can't really improve the back end to it.
You can't improve the back end because you're stuck with it, is that what you're saying?
Yeah.
Right. Yeah. The other big problem, and this is really interesting and not obvious, is that there's a big semantic gap between what you want as a Python person, say, and what the JVM interface offers. There's a semantic gap, and actually the JVM was never designed for compiling Python. Okay, and even when you make changes to the JVM to include, invoke dynamic or whatever it is to help break down that gap, you've still got a big problem. And there's a great paper from IBM from about 3 years ago, IBM Research, where they took their whiz-bang Java JIT, which is one of the fastest JITs around, and said, let's apply this to Python, right? So they took this thing would have cost many, many millions of dollars to build. Maybe 50, maybe $100 million, I don't know. Built over 10 years. So yeah, it's probably more than $100 million to build this thing, okay? So they took this and they bolted it onto CPython and optimized the heck out of these Python programs. And what happened? Well, they got a bit faster than CPython, but they were slower than PyPy. Okay, PyPy is written by a bunch of long-haired academics from Belgium, How could IBM be lagging these guys who just go and build this thing written in Python, no less, right? How could this be? Okay, very interesting paper. These guys took it very seriously and they present this negative result. Our implementation did not deliver. They present the negative result and explain why. And the answer is essentially it's a semantic gap, which PyPy doesn't have, because PyPy is written in Python and it narrows that semantic gap. And trying to build a language implementation that was actually intended for Java and use that to make your Python go fast, essentially the bottom line of their paper is this isn't going to work, okay? This ultimately is not going to work because the optimizations you need for Python are sitting at a higher level. All right, so there's a problem with the second choice. Then you've got LLVM. LLVM is fantastic. It's awesome. It's changed a whole lot of stuff in computer science. But it was never designed to be a back-end for a dynamic language. No way, okay? It's actually not really a virtual machine. It's more a compiler framework. And it's a fantastic compiler framework. But this was not intended, its intended use. And you've only got to go and read the story, the big sorry story about Unladen Swallow, which was Google's attempt to get Python running on LLVM. You go read that story, and it's a pretty tragic story about what happened there. And I've already mentioned PyPy, which is a much more interesting approach to how you build a new language, although it still lags these other implementations hugely. All right, so of course there's an easy fix for all this. What's the easy fix? Anyone know the easy fix? Oh. You just need to invest enough, right? So Java, so how did Java get so fast, given it's got a lot of the same problems as these other languages in terms of being hard to implement? Well, I asked my friends I've got friends at Oracle and IBM who are involved in the implementation of these things over the last 10 years. They've been on these teams for ages. Their estimates are well over $1 billion invested in making Java, getting Java to where it is now. Over $1 billion, okay? And if you look at C and Fortran, the numbers will be even bigger, okay? Ada, even bigger, right? So any language that, these industrial strength languages that we're using have had absolutely massive investments in them, okay? And if you want to make PHP go really fast, probably at the end of the day, you're going to have to start doing that making that sort of investment, among other things. Okay, but the point is, this doesn't come cheap. Okay, it's not by magic that Java, Fortran, C, and so forth perform 10 or 100 times faster than these other languages. Okay, so we've got this big fat abstraction layer. I already showed you it's 35% for Java. Okay, and it's massively higher for Python and Perl and all these other things, right? So how can we ever justify this, right? To me, this is a very interesting question. And the answer's here, right? So hopefully you're all familiar with Moore's law. Gordon Moore said that transistor density will double approximately every 2 years, right? So this is great news. And there he is, there's Gordon Moore, and there's his graph. And it pretty much held out, right? So transistors get smaller and smaller and smaller all the time, just like magic. So our hardware friends are delivering us favors just by magic, right? Very cool. Dennard scaling is the much less well-known but far more important counterpart, Dennard scaling. Dennard said that when your transistor shrinks, both the switching time and the power go down. Okay, that is remarkable. Okay, because that means you shrink the transistor, it just gets faster, and it uses less power. Okay, this is really, really cool, and this is what actually the computer industry wrote off the back of. These two rules is what the computer industry wrote off the back of for a long time. Okay, the device physics guys would come and shrink the transistors. The transistors just by magic would be going faster. They'd be using less power. Fantastic. Okay, happy days, right? So unfortunately, this doesn't work. So this doesn't pan out. There are a couple of problems. Okay, the first problem is this one, right? Unfortunately, the speed of light gets in the way. So if you take this as being your die, a standard die size, and now I'm going to narrow the die down by showing how much the die you can reach in a single clock cycle. Okay, remembering that this is limited by the speed of light, the speed at which you can transmit a signal across a die. Okay, and clearly, the faster your clock goes, the faster the signal's got to move across the die, and the more the propagation speed is going to be the limiting factor. So let's just see what happens. So you end up like this, and this is only projecting out to 35 nanometers. This is old data. So now we're way below that. Okay. So the point is, in a single cycle, you can only go a very, very short distance. Okay. So how do you deal with this? Okay. This is an old story. This is not news. I'm not telling you something that's about to happen. I'm telling you something that's already happened. Well, it's divide and conquer, right? You build multi-cores, okay? So instead of having your die have one humongous CPU on it, you build multiple cores on there, okay? And that's great, except that if we look back to Moore's law and Dennard scaling, Moore's law is still doing great. Unfortunately, Dennard scaling's tanked, okay? And you can go read the literature if you care. If it's interesting on the device physics and what they're doing. What's happened is the transistor is so small that the rules that Dennard was betting on have started to break down. Okay, this is just the device physics. Okay, so you can't actually any longer be getting this thing where by magic the transistors are just getting faster and using less power each time you shrink them. That's not happening anymore. Yes, you can shrink them, but you don't get that power and speed win just by magic, right? So we've got a bit of a problem here. So now I'm going to digress and talk about where performance is headed. By the way, if any of you have questions or whatever, just interrupt. You're also welcome to stretch. All right, so this is a study we did here at ANU. This is, if you want to read about this is written up in a number of places. It turned out to be a bit of a landmark study. We did this giant study of the relationship between software and hardware, okay, over time. And so what we did is we looked at all these different processes, and we looked at how they perform against a whole lot of different software. We built a device that would allow us to measure the current going to the core, to the chip, to the CPU, okay, and we're logging this. And then we go and measure it. We create a matrix of benchmarks. We have native benchmarks like C and Fortran. We have managed benchmarks like Java. And we have scalable and non-scalable. So we've got a good mix. And we weight things equally among those four partitions. Okay, so what we do here, we've got a graph here. We've got power on the y-axis. And we've got performance on the x-axis. Okay, so if things are faster, they're going out to the right. And if they're using more power, they're going up to the top. All right. Now, so there's a Pentium 4 from way back in 2003, and the black square is the mean of those results, and all those little grey squares are all the different benchmarks. Okay, so there's a smattering of benchmarks all over the place there, and they're centered. The center of gravity is where that square is. Okay, and then what you want is as each generation of machine comes along, you want it to be, if you're following Dennard scaling, you're going to be using less power and going faster. Right? That's the idea. And indeed, the Core 2 Duo delivered exactly that. You can see down there, it's reduced the amount of power consumed as it did its die shrink. There's two die shrinks there, from 130 down to 65 nanometer. And you see, again, a spread of benchmarks in the center of mass there. So the question is, what happens next, right? So we want this to keep going, right? What happens next? Well, unfortunately, things didn't go so well. So there's 2008, you've got the I7, and you see stuff going way up on the top right. Not so pretty. That is a new architecture compared to the Core 2 Duo, and if you look down here, we do a die shrink of the Core 2 Duo, which is the same architecture, just shrunk, and you see that it did do the right thing, but much more modestly than we might have hoped. Okay, so the arrow is nowhere near as long. Okay, so the story is not looking so pretty. Are we going to go out here? Well, let's see what happens next. There's the i5 2010 32 nanometer. It's moved to the right, which is great, but it's actually using more power. Okay, so the point is we've got a power problem. How do you solve this? Well, heterogeneity is the slated answer. So instead of building lots of cores, multi-core is solving the problem of propagating signals across the die. Now heterogeneity is offered as a solution to this power problem. Okay, so what we're going to do is on our die we're going to have cores of different power and then run jobs that don't need to use a lot of power on the cores that don't consume a lot of power, and the ones which are performance critical run on the big cores. Okay. That sounds like a cool idea. And in case you're wondering, these things are available today. You can buy them. The system on chips they're quite common. The Tegra 5 has them. They have four similar cores and one slower core. You have the OMAP 5 from TI, which has a couple of big A9s or A7s on there and a couple of M3s, little tiny ARM cores. So this stuff is actually already available. These are things that might be in your phone right now. But this is making its way to the desktop. That's the interesting part. Okay. So what happens though? What happens? So okay, just imagine where this guy on the left there. We've got these two cores. We've got a machine with two cores. What happens? What do you expect to happen if I go and add two new cores to my computer? Two of these slower cores to my computer, right? The idea is that things will be more energy efficient and they're going to run faster, right? That's the idea. All right. So let's have a look. Unfortunately, it sucked, and in fact, it slowed down sometimes by a factor of 2. Right? But on average, it slowed down by 50%. So adding two cores that were slow to our system slowed us down by 50%. Right? Can anyone guess why? Yep.
Because you haven't told it which processes to run on the slow cores yet.
Right. At this stage, that's exactly right. What I haven't told you, but you've guessed exactly right. At this point, we've just got a regular scheduler which is oblivious to two things. It's oblivious to the topography. It doesn't know which ones are fast and which are slow. But it also is oblivious to the criticality of the threads. It doesn't know which one is the one that you really want to be running on the hot core. Now, I'm not going to talk about it today, but the last paper that Ting wrote before she graduated, before she left, finished her PhD 2 weeks ago, addressed exactly that question. Right? So at runtime, she goes and looks at the threads, works out which ones are critical according to how they're using the locks, works out which ones need a big core according to how they're using the CPU, how many stalls they're having and so forth, how much they're depending on memory, and then schedules threads accordingly. And she gets a great result, but I'm not going to present that here. And that's not published yet. She's actually just submitted that for publication. But yeah, spot on. All right, so what happens? Okay, so we've got this thing here which is a resource hog, which is a managed language, and we all want them, we all need them anyway, whether we want them, we need them because they run our phones, they run all sorts of stuff, right? These things that we're not going to escape from them. Heterogeneity, we're probably not going to escape from either because the architects are going to give them to us whether we want them or not. Okay, so what's going to happen? Right, can anyone see a problem here? Okay, remember I just told you that this managed language stuff was only going to work because of this magic of Dennett scaling and Moore's law, and then I just told that's gone. Okay, at least the Dennett scaling part's gone. All right, so what's going to happen now? And our dependence on these managed languages is not going down; it's going up. Right, so that's one scenario. Okay, so what are we going to do? Well, I'm now going to give you 3 detailed talks, very short ones, and I'm going to skip over some stuff here because I'm looking at the time, seeing that we are running pretty late. But I'll give you 3 very quick overview talks on 3 separate projects we're doing here at ANU. Each one of them has been published in the last very short while. These range from, 2 of them have been published. Another one is a new project. The first is this thing called Yin and Yang, which is Ting's work. This is the middle chapter of her PhD thesis. It's work that we did with another student at ANU, Tia Jun, and my colleague, Catherine McKinley, who's at Microsoft Research. All right, so yeah, we start off with this train wreck. So can we avoid this train wreck? Is there some way around here? Well, that's That's our heterogeneous system that we're faced with. The architects are probably going to deliver something like this, okay? A couple of big cores and some number of small cores. So what can we do? All right, so here's a really simple idea. Okay, remember there's 35% of stuff being spent on the managed runtime. So how about this? We run the application on the big cores and put the managed runtime on the small cores. Okay, pretty simple idea. And but for that to work, we need to have a few things going on. Particularly if you actually have these small cores be a bit more special than just being small regular cores. Say they're more finely tuned than that. What you want is ubiquity. Okay, there's no one's going to have a special case for a small core unless the thing you want to run on that small core is running everywhere. Now these GC services like the JIT and VM services like the JIT and the GC are actually running everywhere. You've got them running in your phones and so forth. These are not like special case benchmarks. These are things that are running everywhere, so they're ubiquitous. And you've got parallelism, okay? You've got they've got to be asynchronous and non-critical for this reason we just discussed here. You can't very well have your thing running on a slow core being the thing that everyone's waiting on. Okay? And finally, they've got to be differentiated. They've got to be things which have different behaviors to the ones that want to run on the big core. Okay, so if you're going to partition the space, you want to partition it on the grounds of being differentiated. Okay, so are VM services amenable? So here's the characteristics, ubiquitous. Yes, the VM services are, because these things like the JIT and the GC are actually running everywhere. And are they parallel? Well, yes, GCs and JITs can be made parallel. So that's great, so you can put them on lots of little cores. Are they asynchronous non-critical? Pretty much. Okay, not entirely, but pretty much they are. You can have a concurrent GC, you can have the JIT running asynchronously. Are they differentiated? Well, this is something that Ting went and studied in great depth, and the answer is yes, they very much are, which is really interesting. Okay, not so surprising if you think about what a GC does. It spends almost all of its time just tracking down things in memory. So it's very much limited by memory, not by the grunt on your CPU. So I'm going to gloss over all the amazing stuff Ting did, which is a massive amount of work, which is published in the top computer architecture conference in 2012 at ISCA. It was just a fabulous piece of work, but I'm going to gloss over all the detail and give you the bottom line. How does it work? How does it perform? Well, it performs well. What we see here is what happens when you put the GC, the purple bar, you put the GC on one of these slow cores. If you put the JIT on one of the slow cores, or if you put both of them on one of the slow cores. Okay. Now we've got two cases here. One is the dark one is where we've just added an extra core and bound those services to that extra core, and that core happens to be the same. So it's a fast AMD core. And the other case in the light color is when you add a really slow little core. Okay. Notice the performance. You actually get a performance win by adding that really slow little core. Okay, it's not as good as if you add a huge, hairy, big core, but you do get a win, okay? And power consumption, well, what do you know? The big core consumes a lot of power, but the little core doesn't. Okay, when you look at energy, you get an energy reduction, okay? And when you put these services on the little cores, you actually reduce energy, okay? It means you're using relatively less power to get the job done more quickly, okay? Remembering that energy is the integral of power over time, right? And then finally, a measure which a lot of people think is very important is performance per energy. That is, multiply the two things together because they want performance and they want energy savings. And if you look at that, we get a great result. Okay? So there's a lot. There's an awful lot behind all this work I just presented there, but that's the bottom line, and it's impressive work. And to me, this is one step in the direction we need to go. The next step she took is the one that was the person over here suggested, and that is, what about knowing where to schedule what thread? And she's done another whole paper on this with another student from the University of Texas, and that's being reviewed at the moment. All right, this is the big piece, but I'm going to cut it short because you'll probably want to get to your morning tea. But this is a really fun piece here, and I'm just going to try my best to skim it in a coherent fashion in the next few minutes. This is a piece of work that looks at reference counting. Okay, and the lead student here is a guy called Rifat. He's in the office next door to me in the computer science building there. And another person involved was Daniel Frampton, former student of mine. He's now at Microsoft working on a very interesting project there in product land in Microsoft. And C is another student of mine, and Catherine McKinley, my collaborator I've talked about before, and myself. Okay, you got to start by looking at this. These two old guys. This is the beginnings of GC. It's 1960. Communications, the ACM. Two completely fundamentally different ways to do GC, presented within months of each other in 1960 in the Communications, the ACM, which I find a remarkable coincidence. Okay, so they end up being these two major branches of the literature. One branch goes this way, one goes that way. They start at the same time. Okay. And you probably have heard of McCarthy. He's famous for Lisp, for AI, and so forth. And you may not have heard of Collins, but he was also a fairly eminent computer scientist of the day. So today's GC is ubiquitous, but we've got these two major ideas. You've got this tracing idea from McCarthy, and the idea of McCarthy's is, well, we'll come to it in a minute, but there's tracing from McCarthy and there's reference counting from Collins. However, if you look at production systems, no one uses reference counting except for people who like really slow stuff like PHP and Perl. So tracing totally dominates. Why is this, okay? The essential concepts you need to understand to get anything out of what I'm about to say is that tracing is what we call implicit garbage collection. What that does is it goes and figures out what's live by reachability. So you consider all the objects being a graph. You go and trace that graph from the things that you know are live, like your registers and your stack. You go trace that out. Anything you touched is live. Anything you didn't touch is implicitly dead. Okay, so you didn't go and find the dead stuff. You found the live stuff, and then the stuff that you didn't find was dead. Okay, so that's what they call implicit. Reference counting works the other way around. The way reference counting works is you keep a count on everything that's live, and when that count falls to 0, it's explicitly dead. Okay, so some people refer to this as implicit and explicit. Okay, so what we call naive reference counting changes the count every time a pointer changes to an object. Okay, now if you've ever seen optimized code and you've seen what happens with the pointers changing to objects, they can change remarkably fast, and it's normally done through a register. It's not done in memory. Okay, and so if you're doing an increment and decrement for every one of those, that's an awful lot of memory traffic just for doing very frequent stuff. Okay, so this is not how most people do it today, although this is how it's done in languages like PHP, Perl, and others that use reference counting, what we call naive reference counting. Then there's deferred reference counting. What they do there is they say, okay, let's ignore all these really fast changing stuff and just every now and again go and enumerate all those and do an increment, and then we'll do a decrement later. Okay, so you get the counts right that way. And we'll just do counts for the changes inside the heap. So when you change an object field that points to another object, then you do a change. But if you're changing a register, no, we won't look at that. We'll just look at all the registers before and after and see how they changed. Then the next huge change was what we call coalescing. This is done by colleagues of ours in Israel at Technion, and this is a very, very cool observation that says, actually, you know what? You don't need to track all these changes. This pointer here is changing. It's pointing to that object, that object, that object, that object, and so forth. Doesn't matter. All you really need to know is what it was at the start and what it was at the end, and you can just get rid of all the stuff in the middle and say, okay, decrement the thing that it started out as, and increment the thing that it ended up as. Okay? And just elide all the junk in the middle, which is a huge saving. Okay, that's what we call coalescing. Major changes. Okay, so if you apply all those things I listed, then you get something that's substantially faster than naive reference counting. So what are the pros and cons? It's immediate, which means that once the reference count falls to 0, you can reclaim the thing straight away. So you reclaim as you go. It's object local. Okay, your knowledge is local to the object you're collecting. You don't need to have global knowledge of the heap to be able to decide you're going to collect that one guy. The overhead is distributed. It's distributed in time and by thread. And if you want to build naive reference counting, it's dead simple. Okay? The downsides are somehow you've got to maintain a count. Okay? That has implications for cycles and for space. Somewhere this is going to be this count, right? Cycles I'm using a different sense now. I meant CPU cycles a moment ago. Now I'm saying cycles in the sense of a graph. We've got a problem with cycles in reference counting, okay? You can sustain a cycle of garbage in reference counting, okay? That will self-sustain. You can't ever collect it. So you need some secondary thing to go collect the cycles of garbage, okay? There are some languages around, I won't mention any names, that don't have cycle collectors. They've got naive reference counting and no cycle collectors. So woe betide you if you go and create a cycle, okay? Because it'll stay there forever. All right. But if you want to go and build a high-performance reference counter, they're actually just as complicated as the most complicated tracing collectors. So you lose all that advantage of simplicity. And so the challenge is you've got these two major branches. One is completely neglected. One is used for nearly everything. This one performs really badly, even in its super-duper optimized forms. And this one performs well. Yet this one had nice properties. They're being ignored because of performance. How can we make this one run faster? That's the big challenge. Okay, so I mentioned this. So I live my life inside the GC community. People think this is a crazy idea. Mate, crazy talk. All right, so how slow is it? Well, that's because it's 30% slower. And in our world of optimized systems, 30% is just from here to forever, right? So it's very, very, very slow compared to a tracing collector, okay? But, and it's 40% compared to the best GCs, okay? Tracing collectors aren't the best. The best ones are generational tracing collectors, okay? So it's 40% slower. So Refat's gone and done 2 papers. The first one is down for the count. Very cool paper, which I'm going to talk about very briefly in a moment. And the next one he's just got accepted for publication. It's going to be presented in a few weeks. And I'm going to show you the latest results from that in a moment. So down for the count, I'm going to have to skip over this. I was going to tell you what these lovely optimizations are. They're very nice, but we're not going to have a chance to look at them. But the simple observation that I really wanted to bring home to you for this next section was that Refat made the observation that people have made before in other settings, that most young objects are a special case, right? Young objects mean ones that have only been in the heap for a short while. They are a special case. They account for most of the work, and yet they only live for a short amount of time. It seems like an opportunity to exploit, okay? To special case them somehow, or to somehow or other exploit. And they mostly don't survive, so only 10% of the young objects actually survive. So really you just want to get these things out of your way, right? So, his second optimization is to say, let's start off by just assuming they're clean to begin with, and as we'll see in a minute, they're born clean, which means that we don't, well, I can't unpack this very quickly now, but the bottom line is, by making this observation that these new objects are different, we can get this 16% performance win. And the corresponding optimization, which goes along with it, again with the young objects, is that we can make them be born dead. What that means is, instead of saying that we need to kill them off, we actually need to keep them alive. Okay, so we've inverted things, right? Which makes sense if you think about the fact that only 10% of them are living, 90% of them are dying. So rather than having to go through, so the way one of these systems normally works is with a free list, okay? You all know what a free list is. Okay, so the way it normally works is you do your collection, you mark, and you update all your reference counts, and then you go and kill off all the ones that have a 0 reference count, right? And we flip that around and say, we're going to kill off anything that doesn't, we're not going to go and look at them, we're just going to keep the ones that do have a non-zero reference count, okay? Everything else is automatically dead, because we set the data structures up to be dead unless we specifically keep them alive. Okay, so we just inverted that equation, and that gives us another little performance improvement. But when you combine them, you get this. Okay, so we've wiped out that entire overhead. Okay, so now we're matching tracing collectors. Okay, so this is a very nice result. This is the previous paper. It's like worth an hour's worth of talk on its own, so it was very hard for me to unpack that. But what he did was make these observations about young objects, which allowed us to catch up with tracing collectors. So we have reference counting collectors now performing the same as tracing collectors, which is quite remarkable. All right, but it's still 10% slower than these really fast production GCs. Okay, so this latest piece of work is looks at tackling that problem. So, copying is an important technique in garbage collection, okay? Can anyone see why copying might be useful in garbage collection? Why would you want to copy? Yep.
Defragment the memory.
Yeah, defragment the memory. I just said a minute ago that only 10% of the stuff's alive. If I go and spray stuff all throughout the heap, and they just sort of sit there, splattered across the heap, it'd be much nicer if that little 10% were then moved over there in a neat little package rather than sprayed across the heap. Okay, and this is what's done in most garbage collectors today. To do that, they have to copy, of course. Okay, you have to copy the object over here and put it in a nice little group over there, and you get locality benefits, but you also get space benefits because you're not fragmenting. Okay, so, but this is at odds with everything we just said about reference counting. Okay, what this paper does here is it takes the it takes what we had before using a free list with a reference counter. I just explained to you that reference counters traditionally always use free lists, and ask the question, can we use a non-free list heap structure? Why would you want to do that? Well, because we already know that a free list is about 10% slower in total time than the exact same garbage collector without a free list that uses copying. Okay, and that's purely down to locality and fragmentation. So it buys you 10%. Reference counting, up until right, this month, and up until October this year, for the last 40 years, reference counting has always been using these free lists. Okay, so the question is, can we move them to something that doesn't use a free list? And if we can, what do we get out of it? And the answer is, in short, yes, it does. And what's the result? I'm going to skip over this here. We've got a few little... The result here is these numbers here, which were hot off the press. Okay, this shows you the performance of a whole set of benchmarks compared to the fastest production collector available at the moment. Okay, and what you see there is nearly every benchmark is sped up, 4 of them are slowed down, and 1 of them is sped up by nearly 25%. Okay, so it's an absolute slam dunk. This is one of the best research results I've had in years. Okay, so then this is just from a few weeks back. So what we've got now is something that is unequivocally the fastest collector around, and it's completely counterintuitive. It's using reference counting, which for the last 40 years people have said is a rubbish idea for performance systems, and we've now got our best GC result. Yep. And so what's the story so far? We've got we've moved from a 40% slowdown to something which is faster than the fastest thing in the literature. Okay. Oh yeah, and PHP. So here's a little blog entry from the PHP, the Hip Hop Virtual Machine blog, which explains. So I gave this talk, well, part of this talk to people at Facebook, and they're like, "Oh, awesome! Can we have this in our, in PHP, right? Because does anyone know how many lines of code PHP run inside Facebook roughly? Okay, it's about 1 million, right? And I don't know if any of you have any idea of their electricity budget. This is not a joke, I'm serious. So they've got a massive electricity budget. So if you could shave 10, 15% off the performance of PHP, you could be talking the ballpark of millions of dollars per year, okay, in electricity bills, right? So it's a big deal. So if we can make this thing go faster, that's quite exciting. But we come back to this, and this is what got me started on the beginning of the talk. We find out that PHP has these links back to reference counting, because when they implemented it at the beginning, they built it on reference counting, and they let those semantics, those ideas that are explicitly about reference counting, trickle back up to the language. All right, last thing I want to talk about, and I've only got 3 slides on this, is a thing which we call the micro VM. This is hot work, which has only just started. The lead students are Kunshan Wang and Yilin, and I'm doing this work with a guy called Tony Hosking, who's at Purdue, and Michael Norris, who's over at NICTA. And what is the micro VM? It's a very small, low-level VM, and the idea is it's a substrate for language implementation. Okay, so the idea is you build this little substrate here, and then you can build other languages on top of it. Okay, and we're going to provide just 3 abstractions. Notice these 3 abstractions are the 3 abstractions I talked about before, which are really hard. Okay, we can do this really well. We've got tons of experience in doing this. We've built lots of virtual machines before. We've spent a lot of time building virtual machines before, is what I meant to say. We build these three abstractions, and the memory, concurrency, and architecture. And then we're going to deliver that to people who want to go and build a language like PHP or Ruby or whatever it might be, and they can build on top of this micro VM. How does it look like? Well, it's got an instruction set that's in SSA, which is a form which allows us to rapidly compile it very efficiently to a target architecture. The instruction set supports dynamic optimization, which is very, very important for dynamic languages, so you can re-optimize things, and it supports laziness, so things can be lazily compiled. It's got a very special and simple type system that ignores all the language level stuff, so it doesn't know anything about like a Python type system or a Haskell type system. All it does is have sufficient information so it can correctly compile and can do exact GC. Okay, what's the goal? It's got a goal that we formally verify, just like SEL4 did. SEL4, I don't know if any of you have heard of that. Here's an award-winning paper here from a group. Some of these people are at NICTA just over the road here. Some of them are at UNSW. This is an amazing piece of work here. They did a formal verification of the L4 microkernel, operating systems kernel, formally verified it. And one of the people in that group there is Michael Norris, who's working on the project with us, and the goal we're going to have here is make this little micro VM, which is only going to have in the ballpark of 20,000 lines of code. It's going to be quite compact, actually do a formal verification on it, so we can have a formal correctness. We know formally the correctness of this micro VM. Think back to the problems I was raising before about how the correctness of the VM is an increasingly big problem. If we can deliver that, then that just unburdens the language implementers. All right, Well, that's just a screenshot from a day or two ago. We've got Hello World running on our prototype 01 of this micro VM. It's a Lua client, so we've written an implementation of Lua on top of our first prototype of the micro VM, and we can run Hello World and we can run loops. Awesome. All right. Now, before I finish, I want to remind you why we got down to this little rat hole. We got down here because building languages is hard, right? And it's very, very important because the world depends so much more on software today than it did before, and languages that we have today are broken in all kinds of ways. And I'm on a mission to try and make that better, and there are an awful lot of other people who are doing that with me, and importantly, there are a lot of people who have done it before me. And I just want to pause for a moment to remind you of those who have gone before us all and done this already. Maybe. There you go. Wait, just give us 1 minute, 60 seconds. All right, thanks. So we've got time now for, I was going to try and compress the talk even further, but I didn't succeed. So we have time now for just a couple, yep. And I'll be outside, very happy to answer other questions when we're out there. Any questions? Yep.
Do you write your memory management code by yourself? I mean, from scratch for your micro VM, or you just use the functions inside the operating system?
So we write a garbage collector. This thing will support a garbage collector. We've written many garbage collectors before, and in fact, we'll be able to reuse the code that we have built and tested over many years for building high-performance garbage collectors. So we'll be using that. And it sits at a higher level than what the operating system can deal with. The operating system doesn't understand objects and any of the language level stuff. So this thing will be able to track through the heap and collect objects.
So what about the concurrency?
Concurrency, yes. It'll use, there will be parallel and concurrent, yes. And will it use pthreads? Is that what you mean? Will it use operating system level primitives to do concurrency? Yes, for certainly. Yep, but it may also do language level concurrency as well, and that's something we're right in the middle of debating. And most likely what we're going to do is what we're going to have is end-to-end threading model. So we'll have a number of operating system threads down below, which might be mapped to the number of hardware threads on the piece of hardware available, and then they get mapped up to language level threads via software multiplexing of the threads. Okay, but the GC will probably just have one thread per core that's running GC, and that'll be an OS level thread. All right, thanks very much.
We'll get some